Not of your science. Alright, so guys, this is on page 916, number 38, and for the book deficient out there, the problem is and what they want you to do with this is to rewrite this in the order dx, dy, dz. This is number 38, page 916. All right. Now, without even drawing too much, can you guys tell me what regions this is kind of describing in their areas? Like these two together, could you graph that? What plane would these two together exist in? Let's see if anybody can answer that.
It's y plane. Well, xz.
You guys see how to see that? I mean, the innermost integral is with respect to which variable? Y, right? So then these limits must refer to the xz plane. And the way that this integral is set up is it's looking as if the y function is sitting over the xz plane. So here's my y-axis. The y function is sitting over the xz plane. That's the way they're looking at this. So remember how we talked about it last time? You want to try to figure out what your roof is that's sitting over your floor. And the way that they set it up, the roof is on the y, in terms of the y-axis. Y equals these functions here. And the floor must be this. So a good place to start is to graph the floor by itself, because that's two-dimensional. That's kind of nice to start with something we can totally grasp. And then try to see what the hell's going on with the inner guy. So what would this look like? What would the floor look like? As what does what? As x goes from 0 to 4. Y goes from, not y, sorry, z. Yeah, z goes from 0 to square root of 16 minus x squared. And square root of 16 minus x squared is a half circle. I like it. So what you could do actually kind of is to use the limits in there. When x is 0, z is 4. And when x is 4, z is 0. So you don't get the full half circle. Why not? To get a full half circle, you'd have to let x go all the way down to negative 4, of course, to capture that. So you actually end up with a quarter of a circle. Right? So you can see that before you even do anything, you can see that this is going to be a circle. The limits here kind of even cut it down. This cut it down by at least the top half. And then this cut it down to that corner. Right? Okay. And now, what is it on the y-axis? What is that roof shape going to be? What shape is this going to be? It's going to be a sphere, right? It's going to be a sphere, half sphere, quarter sphere, I don't know. But right now I know it's going to be some part of a sphere, right? So I want to do it instead in this order. So one way to kind of do this is to attack all the limits as they come. Sort of like what we did here, right? So if x goes from 0 to 4, z goes from 0 to 4, really, overall, right? That's the outputs that you can get for z. What can y then do? What numbers come out for y? I mean, what's the highest this guy can be? 4. And of course, when you put zeros in there, you get 4. When you put a 4 in for either one of these, you get 0 up there, right? Okay, so you might want to try to graph something three-dimensionally here to help you out a little bit. Right? And the funny thing, the beautiful thing about a sphere is that it is symmetric with respect to the variables. It actually doesn't care necessarily which variable is where, as long as it ends up in the right place. So if you realize that, this problem is actually very simple. No matter what's on the outside, like we just said, now DZ is on the outside, right? And what did we just say about Z, about any of these variables actually? Where do they go from to?
0 to 4.
Yeah, in fact, you can see it right here. Z's got to go from 0 to 4. Unofficially here it goes from 0 to a function, but what are the actual numbers that can come out for Z? 0 to 4. Right? So there, I've already got the outer part done. Now the next part is just to figure out how do the variables change in here. This is a circle, this is a sphere. They really don't care too much about the variables themselves, to tell you honestly.
It was kind of confusing when we have two variables. All we did was we solved for the variable we need. Kind of changed the equation. Here,
Sure.
I guess that doesn't work.
Well, to an extent it does. What's going to make this a little bit easier is if you try to graph this thing three-dimensionally first, right? So get a trace of the floor, try to give yourself a rough sketch three-dimensionally. What would this thing then look like? So if you try to get this three-dimensionally, we've already got part of this. Here's my XZ plane. So we've already got this in the XZ plane, right? So actually on the picture now, it's kind of turned around. So it's 4 here, 4 there, and it goes like this. So there's that there, right? Now this is the upper part of the sphere here, right? And of course Y, what's the highest Y can be? We already figured that out. Like the whole thing's got to be out to 4, because the whole thing is really governed by this sphere.
So it goes this way.
Yeah, so now it's going to be 4 there. So somehow that's going to factor in, right?
But that's going to be in ZY plane then?
Well, you can try to trace it in the ZY plane, right? What is happening is if you graph this whole sphere, you really just want the part of the sphere that's sitting over this region here. That's the main thing here. That's the roof. As the way they've drawn it now is that's the roof sitting above the XZ plane. So if you drew this whole thing out, it would be a complete sphere. What do I really want though? I want the part of the sphere that's over this floor. So I just want the part of the sphere that's over just this piece here. So I'm taking this entire ball and I'm just cutting it to be, let me see if I can possibly, well, let's see, I can at least do this, considering my scale sucks a lot, but that's too bad for me. Be a lot easier in isometric, but that's all right. So I got this attempt at a sphere here. And of course it would be three-dimensional, but I just want, I don't want the entire sphere, I just want the piece that's sitting over this floor, right? So it's going to only exist where? In the first octant. I love it. Cool, right? So this thing has got crazy symmetry, which actually makes changing the order of integration a lot easier than normal. Because all you have to do is figure out which variables should go in places now where they used to be like this, which variables should go in there now that you're looking at it like that. So now what do I want to be the roof? And what plane does my floor live in now? At that level, I want everybody to be with me on that. Cut off the middle integral. What's the middle integral? dx. So where's my floor going to be? What plane? YZ. 11. So my floor is now going to be in the YZ plane. And now over that I've got a sphere, right? Maybe.
Which is Y.
But trust me, the piece that's missing here, it's a little, of course, difficult to do up here, is if you graph this three-dimensionally, just graph the part that you want, it'll be a little bit easier to pick out the limits for each variable. Right, I can't quite do 3D up here on the board
So
well.
if I'm looking YZ plane.
I want the YZ
goes
plane to
from
be my
0 to
floor,
4,
right?
up. But equation is right there, so we can use the same equation.
I like it, exactly.
Which is the.
Yeah, so
16 minus-
y is equal to square root of 16 minus x squared minus z squared. So x squared plus y squared plus z squared equals 16, right? Or 4, no, 16, yeah. And now, what do you want the inner one to be in terms of now? I mean, not in terms of, but what do you want to solve for the inner one now? This one was, of course, solved for y. And now I want this inner one solved for x. Yeah, cool. So x equals the square root of 16 minus y squared minus z squared.
But what would you use for y then, for dy?
Now, the nice thing about dy dz is, what is this thing going to look like in the yz plane is really the question now. Because here, this was easy. This piece, I just have to figure out, do I want to go this way or do I want to go that way? And they pretty much gave it to me already this way here, right?
Yeah.
Switching those limits would be easy as hell. Because all I'd have to do is, instead of going, letting x be pure numbers and z go from this, I could let z be pure numbers and let x go from 0 to the function, right? That would not be a big deal. If I can draw this picture for my floor, the way it is now, my floor is now yz, then it'll be just as easy, right? What will it look like in the yz plane now? That's really what the question is. Here, I get y goes from, z goes from 0 to this. So you get this here, which is really what this is here, right? That's what this is here. And of course, this forces it to be only here. Okay, cool, right? So you want to do a similar thing now with the YZ plane, right? My floor is going to be what I do my arrow drawing on. And so right here, this is where I want to be able to draw y, z, and then I can just figure out my arrows. Which way do I want to go with my arrows?
So since it's a sphere, we can make up an equation z squared plus y squared equals 16 also.
Yeah, exactly. Z squared plus y squared must be
So
16.
if we stretch it this way or this way, it's the same.
Yeah, so this is not really that bad. So I'm trying to, at the same time as I'm trying to do something general, how to attack any problem like this. I'm trying to show you this problem really isn't that bad. Because now, instead of this equation for x and z, what do I have for y and z? Z squared plus y squared equals 16. Because I want that plane, I want that trace, right?
Yeah, I was confused. How did they solve for y if there is no y there? That was my question. I guess that's
That's it. They took this piece because it was the XZ plane that I was doing my domain, that I was doing my region of inputs. Now I want the YZ plane. And this is a sphere, so I just get this circle in that. So my middle integral is dy. So, of course, y goes from 0 to what now? How do I get that? Yeah, this is going to be the square root of the top part of that. 0 to the square root of 16 minus z squared. And we already figured out the innermost. X was easy. From this, we got the general equation, which we solved for x. We got this guy. Oops. So you notice how really I had x's and z's in here before? And what was the innermost integral? Y. So I had x's and z's. Now the innermost integral is x. So now I have y's and z's. That's the symmetry of circles and spheres, making this a lot easier than in general. In general, it's a little more difficult. But here I just use the symmetry. You just got to figure out where should y and z go. This inner one's easy. This one not so easy, but still, look at the symmetry here. This is an x. What's the next integral out? Dx. So what should go here? What's the next integral out? Dz. But really, there's two things going on. You can draw the pictures. Even though 3D, even if you have isometric, is still not the best in the world, you still want to try to do it. at the same time, you could be looking at what exactly do the limits tell me. Y goes from 0 to this. Well, I can solve this and then use that for some other variable. I can solve for x, solve for z. Okay. And don't get me wrong, I'm not saying that this kind of stuff is easy. This particular problem had shortcuts to it because of the symmetry. This kind of stuff is difficult. I'm going to be honest with you. I mean, trying to, given an integral in a certain way, switching the limits is actually decently difficult in general. Because it's very easy to go on the wrong side of a function, like you guys saw even in 2 dimensions. Instead of getting this part, you got inside the parabola, and that's easy to make that mistake. What you really want to focus on is graphing the pictures, traces, 3D images, and then trying to work with the limits. Together, looking at the pictures, looking at the limits, what functions you actually have, those together should help you figure out what the limits should be. Yeah.
So if we go ahead and solve the integral, we're not jumping into polars yet in this section, but it seems like it's easier to solve with this polars.
Oh, hell yeah. Did they ask you to actually, and then evaluate? Cool. I like it. The nice thing is, when you integrate this middle integral, you're going to get an x here, right?
Yes.
From 0 to this.
Which is going to be the 16 minus.
Yeah. And if you do the next step, so let's see now, if we do that integral 0 to alright, so what is it now? D x, y, z. So the inner integral is going to be just this here. You get an x, so you just get this here. Now, notice what this is. Now, here's the cool part about this. Of course, you are definitely not going to use the word cool. And I don't blame you too much. What this really is square root of a constant, which in this case, the constant would be 16 minus z squared. Minus y squared. What does that entail using to do this integral?
Use the triangle?
Trig sum. Using a triangle to do trig sum. Aww.
We're so good, never have to do that again.
So to make up the ones, because it looks like that's the hypotenuse 16 minus z squared. And is that going to be, would that be right?
So this is in the form a squared minus x squared, right? Right, this is your constant, this is your variable term.
Yeah.
So I don't know if you guys, I never really memorize much of anything if I can help it. I just kind of reason it out when it's given to me. So what would make sense here if I used...
Because that's a 16 minus z squared, that's the hard part to put it. Can I put 4 minus z, that's it?
Of course not.
That's not going to be.
Of course
right?
not, yeah.
That's what I'm saying.
It'll be the square root of 16 minus z squared, yeah. So your a in this case is going to be the square root of 16 minus z squared. Right? What trig function are you going to use? I'm always hopeful. This is the constant, right? So here's what I do. I never memorize this stuff. It's just too much crap to worry about. What are my usable trig subs I can have? I can have 1 minus sine squared is cosine squared. And that's the one I want. I've got a constant minus a function squared. So I want to let x equal to a sine theta. Right? If I had a constant plus tangent squared, right? And of course the other one is secant squared minus 1 equals tangent squared. So if I had a function squared minus 1, that's when I want to use secant as my replacement. Right? If I have a constant plus a function squared, that's when I use tangent as my replacement. And of course here's the nice one. If I have 1 minus my constant, my function squared, that's when I want to use sine as my replacement. But if you guys just want to memorize that, cool. Right?
I usually don't remember. I was using, I guess, different approach. Like I draw a triangle and
Okay.
find all the pieces.
Gotcha. And it should kind of match up with this.
Yeah, usually.
And it might not perfectly match up because this is a very generalization. You can actually do some more specific substitutions that would work better for a certain problem. But this is in general what to do. Yeah. Yes.
Can we switch that to polar coordinates?
Officially, at this point, I think this is from 13.4.
Yeah, that I need right now.
Yeah, actually 13.3 is where we did polar, right? But this is a triple integral, which would actually be cylindrical, at least, if not spherical, which we barely talked about. So that would be from the next section, yeah. So officially, no. But to tell you honestly, the first integral is easy, right?
Yeah.
Now I would switch to polar. You could switch to polar here. Now that's no longer
yeah,
triple.
yeah, this is what I mean. Yeah.
Yeah, cool. Switch to polar there. So this is not impossible. There is a reason you were taught trig sub. It does happen. It happens a hell of a lot more than sine cubed, cosine squared crap. Trig sub happens a lot more often just because it matches formulas that we use in engineering and physics. That kind of thing happens a lot. But in this case, you see why polar kicks ass, because this would be nice. Y and z are just dummy variables. Who cares? So if you don't like y and z, make them x and y. Who cares? Because now you have 16 minus x squared plus y squared, basically. So that would be r squared. Yeah. And then you have an extra r on the outside, and then it's a u sub away. Cool. Because I don't think they said you can't use polar. Right? You just have to do that first integration step, which is not a big step, because you don't know triple integral polar analogy yet. We barely talked about that yet. All right. Wow. That was a neat one. Any other questions from homework? Oh, I don't want to ask you anything. I think last time we did talk about cylindrical, and I'm hoping and praying that you guys realize cylindrical is not a big deal at all. They said, what's the easiest way to go three dimensions from polar is just go, use z. And then, of course, they call it cylindrical because if you pick a circle up, it's a freaking cylinder. So that makes total sense. The one that we barely got into last time. Is this thing. You put back up here what these kind of related to. Now, I want to show you something really quickly that'll actually make these a lot easier to remember. Take a second from what I've written up here. Figure out what x squared plus y squared is. Figure it out. From what I've written, what is x squared plus y squared? Don't say it out loud. Just work it and then sit on it for a minute. plane. What was x squared plus y squared before? In just polar.
R squared.
R squared. So do you see how this is not perfect, and I always look for the ideas that make sense, and this is really kind of what happens here. What was R now goes like rho sine phi, right? Rho sine phi is now what R is. So what was x in polar? R cosine theta. So if R is now rho sine phi, doesn't this make sense? R cosine theta. R sine theta. And then z gets the other piece of rho. So who remembers here, coming back on top of this, I've got this up here. It's going to make it maybe, hopefully, a little bit easier to see. Rho is basically the nicest piece of this. And theta. They're basically the same as before. What's rho? What was R? How far away from the origin? So what's rho? How far away from the origin? Same thing, just now I've got 3 dimensions to play in, right? And theta is the same, exactly the same as it was. Theta is stuck in 2 dimensions. So theta is purely in the xy plane. Do you see that? So here's theta. It just turns things around. So it actually does exactly what it used to. Theta used to just say, turn here. And it's the same damn thing. But now, the new thing, phi, with the z-axis, what does that tell me?
That's also in 2 dimensions that we look like different dimensions.
True, but I'm just saying theta is like in the 2 dimensions we're used to. Phi now is going to be this, and actually it's not quite as stuck, because if I turn theta around, phi does go all the way around. But I know what you mean. So here's phi. Phi just tells me how far away from this positive z-axis I am. So if phi is 90 degrees, where am I? XY plane, right? What's 90 degrees away from the positive z-axis? XY plane. Cool. Now here's what I really like. This is the hard part about this. Learning a new coordinate system actually means you have to learn new basic forms of graphs. Like we all know what x squared looks like. We all know what plane looks like in 3D now. But you'd have to know, if I made phi a constant, what kind of shape would that be? Holding the other two, they can be whatever they want to be, but I got to hold phi to be a constant, which means I can't turn away or come closer to the z-axis at all. But theta can be whatever it wants to be, and rho can be whatever it wants to be. What shape will I end up with? A cone. I love it. So sure enough, if I do that, if I say constant phi surface, I get that. Yeehaw! And like I just said, if phi is pi over 2, which is basically 1.57, I get the xy plane. All right, at least my little circle lies in the xy plane. Shoop. Okay. So what would a constant theta surface do? If theta is constant. So here's theta moving around. Yay. But now if theta is constant, and I let phi change, and I let rho change. So if I let pop, gotta be careful. So theta has got to be a constant, is what I'm saying, right? If theta is constant, it can't turn. It can only go up and down and out. So it's going to catch this half plane here, right? That's what that's going to be. Okay, and of course, if rho is constant, this is the easy one. In polar, if r is constant, what's that? R equals 2. It's a circle. Rho equals 2 is a sphere. So sure enough, if I have a constant rho surface, bam, there's my sphere. Neato. Small, big. All right. I can turn them all on at once and really get a freaky looking thing. Yeah. Yes, ma'am.
You said it was a half plane for when what is constant theta?
Theta.
But can't rho be negative also, or no?
Let's see, wait a minute. There. Okay. Sort of the same thing with r. It can be what we normally assume it isn't. So I mean, if theta is a constant, and this is really just then rho going from 0 to infinity. So technically you could define rho to go from negative infinity to infinity and catch the whole plane. Good. Cool. Alright. And actually, down here they define it.
Okay.
Yeah.
So if it went from negative infinity to infinity.
Then you catch the entire plane that sits at that angle in the XY plane. Cool. Alright, maybe. Okay. So the next thing to do is to figure out what happens when I try to integrate in spherical coordinates. So we know what happens when I try to integrate in polar, right? Just going back for a second to polar. That would be, what's the, at the end here? R d theta. And the extra r is really just because r d theta is the length of that side of the polar rectangle. Remember the r theta is the length of an arc? So to get the area of that polar rectangle, I need the length times the length. So dr is the length here. R d theta is the length here. So when I multiply those together, I do get the entire area. To me, it was really a mystery because my teachers never really taught me any of that. They just said, this is what it is. I'm like, why is that frickin' r in there? What the hell? And that gets even worse in spherical. You pick up more shit in spherical because in spherical, you got to go in the other dimension. You got to add another dimension to your area. You got to add another one coming up. And it's going to be dependent on angles and stuff. Great. Yes?
Can you explain that again, why there's an R there?
So, I don't know if you remember this, but this was, this length here was delta r.
Okay.
Because here's my origin, I'm going out, so I can make it a little bit better by going in like that. So here's my center. So that's delta r. And remember, I'm letting this get really small, so it doesn't, I'm kind of doing this in the center, but it's still, this side, the side there, this is delta theta. What's the length of that arc? S equals r theta. So the length of that here is going to be r delta theta. So what is the area of that polar rectangle? R delta theta times delta r turns into this in the limit when you let your rectangles get really small. Do you see that? So that's why I'm hoping it kind of makes sense what has to happen for 3 dimensions. In 3 dimensions, I'm going to have this same problem here, but then I'm going to try to add on top of this, I have to add, that's not terrible, is it? I was kind of worried there, but okay, now it's getting bad, Jeff.
It's pretty good.
That's not bad.
It's pretty good.
Come on. Shit, for me, that kicks ass. Now I've lost it. But you guys with me, that's a little polar rectangular box now, right? So there's a couple things we got to be careful of. I'm going to desperately try to explain why this is the way it is. And actually, part of it is easy. This area down here used to be, and I'm going to say that and you'll see why, r delta theta, right? R d theta. That's the area of that polar rectangle. It used to be that. Why is it not that anymore? What does r basically become now? Rho sine phi. Right? Stay with me now. Stay with me now. Because watch, here's a really cool picture. Not just because it looks like I'm hammering something when I do this. Boom. But let me see if I can bring this around so we can see it. It's not terrible, but it's not. Get this way out there. All right. Freakiness. I'm going to try. Okay. So what I've got here is basically there, right? So at the base, in the XY plane, it's the way it was before. But when I pick it up, do you guys see how if I picked it up all the way, it would be nothing. It would sit on the z-axis. There'd be no area. So it's got to be somehow dependent on phi. And sure enough, r used to be just all the way, but now r is going to be rho sine phi. That's what r is going to be in the xy plane now, rho sine phi. That's why it's got to show up. So now the area of the base is going to be rho sine phi delta R, delta theta. Good Lord. Okay. Now, what am I missing to get a volume? All I'm missing is this new height. If I can figure out the height, I can multiply and get the volume, right? And then I can triple integrate over that volume. That's the whole idea. Okay? So what is this height here? On this one, it's this red line. Oh, let's see where they have it. Too bad for us, they don't. But, let me make sure I'm looking at this correctly. No, oh, here it is. So now this height is here. This is my base. This is my area of the base. Here is my new height. And if you think about it, it really just makes sense. It's my hope. Let me make sure I actually got it in the wrong place here. No, I don't, but it's just not the same as that too. Let me just refer to this. It's a little easier to see it here. This is delta phi, of course, right? That's how, because that's related to the z-axis. That's delta phi. So what's the length of this going to be then? What's the length of this side? If I know the angle, how do I get the full length? I got to multiply the angle by the, in this case, rho. So this arc length that is the height is now right here, rho delta phi. So this height is rho delta phi. Which is why you end up, at the end, you end up with, putting this all together now. So the volume here is really, so I ended up with, yeah, that's good. Let's see, dV is really going to be, where'd it go? Rho squared sine phi delta R delta phi delta theta. Multiplying that height by that area. Is that going to be the volume of the box? So we got everything in the right order. I think I did. So now to get a full volume then, the limit during the limiting process, hopefully I can kind of skip the whole Riemann sum idea. And the limit that my little boxes go to infinitesimally small, I get this triple integral. Oh, I have an R in there, my bad. Sorry guys. So that should be a rho.
So we get another row? Like 3 rows?
No. This is the volume, delta V. This is delta rho. Yeah, delta rho. So 1 rho sine phi is just so it's the R. It's the R, what used to be the R. The other rho is so it can multiply by the d phi to get that side length, that arc length for that side. And then the rest of it is part of the area that we had before. I mean, you can kind of see where things came from polar, 2-dimensional polar, to 3-dimensional spherical. It's going to have to get a little uglier because it's going to have a whole new side that has to be an arc length. So it picks up a couple extra things.
So on that one down there, when you said used to be, when you change it, it's not delta R, right? Down there?
Oh yeah, thank you.
Okay.
That's where I messed up just a minute. That's why I put an R there. I was trying to figure out why I put an R there. Yeah, it should be a rho. Yeah. All right.
So that's like that tail that we usually add R dr theta. Now we
Exactly.
add
Now you have to add this automatically when you're trying to do spherical coordinates. Let's try one out. And then I got a little 13.5 quiz. We'll take a break and then we'll try to do 14.1 because to make it official, I'm going to make the last 2 sections in chapter 13 extra credit. One of them's already extra credit. I'm going to make the other one extra credit because it's not as important as chapter 14 is. We're desperately going to get into chapter 14. So let's try one problem out. Page. Let's see. Dallas Gross. Page 931. Number 40. Unit circle, we know unit ball is just the spherical analog of that, right? It's just a sphere raised one.
There's
So they mean when they say unit ball.
inside.
No, it's not on the boundary of it, it's when they say ball, they mean the whole thing.
Like the sphere itself.
The outside and the inside, so it's filled in. Right, this is not a boundary interval yet, thank God.
Does it
The
really
interval of
say
the whole
ball
region.
or it say sphere?
It says ball.
Oh, okay.
Yeah.
Mine says sphere.
Oh, yours is sphere?
Yeah.
Good. They always would change that because sphere makes more sense. Alright, so first thing is, realize as always, this has nothing to do directly with the limits, of course, right? That's the function I'm integrating over. What am I integrating that function over, though, is determined by the region I'm talking about. So how would this unit ball be defined by my spherical coordinates?
You have
So
constants.
z goes up to 1.
So, and to really hammer this home, this really should always be in exactly that order. D rho, d phi, d theta. So I know at the end of this, I can go ahead and put my rho squared sine phi d rho d phi d theta. All right, that's going to be at the end. It doesn't have to be in parentheses. I don't know what I did. So the innermost one is going to be all about rho, and that should be really the easy part. Careful. Just like r, rho doesn't ever have to have the negative part, because that's going to be included when I do the angle. The angle will make sure I get all the way around, right? So rho is 0 to 1 because it's the unit sphere. The next one out is phi, or phi.
Are we doing 0 to 2 pi now? So everything?
Now here's the weird thing about
Or 0 to 9?
here's the weird thing about phi. If I go all the way around, and I also go all around on theta, won't I be counting some things twice? Let me see what's a good way to show this picture. If I go, what's a good way to say this? If I just go from 0 to 180, and then I let theta go from 0 to 2 pi, won't that capture the whole thing? You guys kind of with me here?
Yeah.
If I go, let me go back to the other picture, maybe that would be better.
That will make a perfect sphere.
No, it's not going to work the way I wanted it to. Damn. I was hoping they would keep it open. Too bad for you, Jeff. All right. Well, that's not quite what I want. Okay, anyway. This might be a decent picture to talk about this, though. So if I let theta go from 0 to 2 pi, all I need to let my phi go from is 0 to pi. Because then when I rotate it all the way around, I capture the whole thing. Right? In fact, here's what I want. Here's what I want right here. Here's the sphere. I'm not going to make a unit so we can all see the damn thing. If I let phi go from 0 to pi, and theta go from 0 to 2 pi, I am going to get that whole sphere, am I not? Yeah, so if I let phi go from 0 to 2 pi, I'm actually kind of like double counting some areas. So almost always, phi will go from 0 to at most pi, because the theta is the one that comes in and makes sure that it sweeps out the whole thing it needs. So here, this will be 0 to pi for phi. And then theta, of course, has got to go to capture the whole sphere. I've got to go 0 to 2 pi. And now you throw in there the function that you actually want, but we change it over to spherical. This will be, what is that now in spherical coordinates? Rho squared to the 3/2 power, which is rho to the 3rd, right? So now we get this. We get integral, 0 to 2 pi, 0 to pi, 0 to 1. E to the negative 2's cancel, rho cubed. Thank God there's a rho squared out there to help me do what? U sub, I love it. Because now the derivative of this is in there minus the constant, which I can make cut happen. You guys see that? So a lot like that R came in and saved our ass for polar. Sometimes I needed an extra R, so if you forget it, you were screwed. That rho squared is going to come in and save our ass. Obviously, though, just like any integral, this could lead to something it's impossible to integrate, which you would need series answers for. But for right now, they're going to, of course, thankfully keep it to things that will end up being integrable. Many of them should be U sub bubble, right, just to make up a new adjective. So this wouldn't be that bad to finish out, right? If you do this. Say so, Jeff. Let me see if you guys can handle this. If I do U sub, U would equal this, du would equal 3, negative 3 this, right? And to get that negative 3 to show up, I'd have to have an over 3 out there. So I get that. And of course, this is from 0 to 1. Just to check myself, if I took this derivative, this will be this times negative 3 rho squared. The negative 3 would cancel, and then for the rho squared, there you go. Cool. Exactly what I wanted. So the less you actually have to do U sub work, the quicker your problem will be. Of course, if you're not all that comfortable with it, show the work. And this is not too bad. Now be careful. Some of you guys forgot. Just because there's a 0 limit doesn't mean you can just forget that part of it. Because especially when there's e's, when you put a 0 in, you get 1. In this case, negative 1/3. Yeah. So don't forget that piece of it. So when you throw a 1 in there, you get negative e to the negative 1. And when you throw a 0 in there, you get negative 1/3. So minus that is this. Oh, I already did my d rho. Sorry. That's gone. Now this is all a constant, right? It's an ugly ass looking constant, but I don't care. So the integral over phi is not that bad. Right? Just integrating constant sine phi d phi, so that's easy, right? And when you plug those in, you'll have another constant that you can do over d theta. Okay, so not too bad there. So you'll
E, right?
Say again?
Is that an E?
E here, yeah.
Oh, okay.
Sorry. So you get negative e, negative 1 over 3 plus 1/3. Integral of sine is negative cosine from 0 to pi d theta. I'm hoping this is the part you guys can just tear into. I mean, this is very nuts and bolts, just have at it, right? It's setting up these damn things that are freaky. And then finally you get, let's see now, I get negative this business times negative 1, so I get this business. You do it, Jeff. And then I get minus negative, so plus this business times 1. So I get 2 of these. You guys see that? Cosine of pi is negative 1, so you get negative negative is 1 of these. Minus and negative is plus, and the cosine of 0 is 1, so you get another 1 of these. So I get 2 of these at the end. And then that integral just picks up a theta. Multiply this whole crap by 2 pi, you get 4 pi times this weird thing here. Okay, which is hopefully, I don't know where oh, that's right. This is a book problem, so who knows. And don't forget, once you get to a certain level, I don't know if you guys have played around with Wolfram Alpha, but it actually does multiple integration. And it actually lets you put in function limits if you have to. So it's a beautiful way to check your homework as you go along when you hit those kind of things. So let me give you this here. Let's at least get started on this thing about 13.5.
Oh, okay, no. I didn't. Oh, sure. I think it's because he's never done a problem. That's why I'm shocked.
What do you mean?
We did a homework problem.
I did, cool.
I told her we didn't homework, and she's like,
Nah.
we're
I was
doing
like,
it.
no, we can odd. And I was like, wait, hold on.
She still doesn't know that you're sniping.
No, it's because I was shocked. I'm still in shock that he did a homework problem.
I know what you mean. Yeah, it's a gimme there.
Did you say 15.7 is also exercise?
What's up?
Which one did you say?
Oh, the last 2 and 13, so
Oh, 6 and 7.
there you go. And you can pause that and look at that business. There's the answer over there. I need a...
It's been a while.
Alright, so hopefully everybody realizes one side is 14.1, we haven't talked about that yet. The other side is 13.5. So take a look at those.
Tornado?
No. Yes, it's a tornado.
I have no idea.
These are tornadoes. Oh, sweet. Exactly.
So you say tornado.
Woogity.
What?
What is that?
Sign language? Tornado?
Really?
Yeah.
Like the Doppler thing about the winds going the other way quickly. Well, you're not
Really?
Yeah.
That's how you know there might be a tornado, is when you look at the Doppler, you see winds going the opposite direction quickly. That's a location of a tornado, so it makes sense that that's the sign language.
Yeah. I always wondered, I was like, why isn't it like this? You know, that's just how I would make a tornado with my fingers. But no. Woman?
Crazy.
What is it? Is that the real sign?
No, like woman.
No, come on.
This is woman.
Yeah, woman, yeah.
Oh, okay.
This is girl. This is boy. Old. I remember a few things.
Do you remember this?
What the hell is that?
What was that?
What was that?
Sandwich
Sandwich
now.
now.
Oh. I love the signs for want,
Yeah.
now.
Oh, it's now.
So if I'm a little kid, the teacher, my parents teach me sign language, I'm like, hell yeah, I'm gonna say that all the time. I want it now. So wait, sandwich is sandwich.
Now.
Oh, now.
Oh yeah.
Just because it's
I just made something useful.
It's sandwich. Sandwich now, woman? Damn it! Sound like woman.
Deal. But that tone.
Yeah.
I like this now. You do it with your facial expression. Just like the first So you gotta do the backhand. There you go.
Is there a sign language for this? Does it
It means you're slapping somebody.
That's fun. That's what I do with the sign language, you just go, what about this? This.
Like, you walk away.
Good definition, certainly.
You walk away from.
So bad.
That's what laughing at you.